although it's a single crystal, but the surface itself is a defect. You can imagine that we have a periodic crystal of a single crystal. The periodicity happens perfectly, but it eventually going to the end while it match the surface of the crystal. So we can also see the surface of the source of the broken symmetry of the translational symmetry. So those surfaces are also can be seen as lot of local states at its vicinity. Alright. So while we are drawing our band structure, if the crystal is finite, there's actually lots of levels in the middle at the surface because there's where the translational symmetry ends. Alright. So if we see from the perspective of each atom. For atoms in the bond crystal, each bond there's all the bond is connected to the other one. There's no other point defects. However, for the atoms at the finishing surface, there will be some bonds that connect to an atom. So it becomes a state that your carrier, either electron or hole, can be trapped at the surface. So the general mechanism is the same with the Shapley-Hall recombination. But the only difference that only happens at a position near the surface. So if the carrier is away from your surface, the surface recombination doesn't matter. But if it is, then the carrier near the edge of the crystal usually has a low efficiency. So there's an important term is that first is what's the diffusion length of your carrier above crystal. If the average diffusion length is equal to L, we can make a simple approximation, which that for the carriers between the surface and the L, it is likely the carrier will be trapped by the Lagrange bond according to the diffusion. And if the X is larger than L, then the surface recombination doesn't matter. Although this is a brutal division, but generally right. Yeah. So the carrier density divided by the non-radiative time is the overall non-radiative transition rate. But for surface recombination, we need to consider how much how big the overall volume will be included for the surface recombination. So it should be proportional to the diffusion length as well. That will be more reasonable for the total recombination, surface recombination devices. So the original change usually is N over tau. It should be written as N times L divided by tau. And the length divided by tau is a unit of velocity. So the surface recombination is usually called the surface recombination velocity, not the surface recombination rate. It doesn't really mean it's competing the electron, it's velocity crystal. It's an overall notation that clearly describes what's the dynamic of the surface recombination. It's not only about the lifetime of the carrier, it's only about the diffusion length of such carrier. So that makes the surface recombination pretty geometry driven. For example, if we're making a vessel with a dimension d, if the vessel becomes smaller and smaller and smaller, then the surface recombination will become dominant. But however, if you are making a larger ship, yeah, there's still some surface recombination. But however, the area to volume ratio is small, so it doesn't become another a point anymore. So the recombination rate need to be rewritten with a rather simple modification. In the short theory hole, we write it as n over tau. For surface recombination, we should write it n times Vs, and the Vs we call it as the surface recombination velocity. So we will replace the original original tau with 1 over Vs. Then the total surface recombination will be written. So after replacing tau, those tau as 1 over Vs. Okay, so the tau x become 1 over Vh. The tau e become 1 over tau e. And the terms of the area divided by the total volume. So if the area volume ratio is high, that means with the same the device volume, that's a very high very dense of area which the surface recombination happens. So your device will undergo a serious non-radiative transition as well, even though the crystal quality could be pretty good. Okay, so the surface recombination is very material dependent. This is the Einstein's relation called between diffusivity and the electron mobility. We call it the D is equal to mu kT over Q. So the diffusivity is proportional to the carrier material as well. Yeah, this is the magic equation, also an Einstein's invention. We like meet Einstein's invention everywhere. Alright, so we can compare the carrier mobility of some common semiconductors. For example, for gallium arsenide, the mu e, the electron mobility with intrinsic doping, and the undoped case, the carrier density is the mobility is pretty high. It could be 8,000. Compared to gallium nitride, the gallium nitride, the carrier mobility is much lower. It's usually this is also doping and the quality dependent. The higher the mobility, the better the quality, better the crystal quality, or lower the doping level. Anyway, some might get 400, 500, maybe even 600 is possible. Very good crystal. But anyway, compared to the gallium arsenide or indium phosphide, the value is only 1/10 for the carrier mobility. So, because the gallium nitride has a rather low mobility, carrier mobility, than the gallium arsenide and INP, then because the L, the diffusion length, is equal to the D times tau, right? If you learn the semiconductor device physics, if you don't, you just accept this truth. And the D is equal to mu kT, so it's equal to D mu k tau divided by Q. And the L over tau, the velocity is equal to, so divided tau, the tau is original here, so it should be something like that. It's a mu K Q tau. Okay, so a material with high carrier mobility suffers from a severe surface recombination. So this is also a image I found it from a review paper. I think it's good because it covers so many kinds of materials. For material with high band gap, like gallium nitride and indium nitride, the surface recombination velocity is low due to its rather low intrinsic carrier mobility. Why the ingot has even a lower carrier, a lower surface recombination mobility? That's because for alloy, for material with a compositional fluctuation, the carrier will be scattered by the irregularity of the atom arrangement. For example, for 50% indium and 50% gallium, does the indium gallium arrange like indium gallium, indium gallium, indium gallium? No, it's some kind of randomness between them. So those randomness also lowers the carrier recombination, also lowers the carrier mobility due to alloy scattering. So the mu further reduced. So the ingot even has a lower surface recombination rate for the GaN. On the other side, you see the gallium arsenide has a really good carrier mobility. So that's how your cell phone operates with such high speed. But there's a problem that if you make a device very small, you have a problem with a very high surface recombination issue. So this is surface recombination is a big issue for device with small volume, like a micro LED, very small VSO, nano wire, or even the photovoltaic, photovoltaic device, 太阳能电池, surface recombination are all very point of interest. For lasers, it's just something we need to take a look, but probably not the major issue we have now. So how does the surface recombination might be improved? Usually you don't have so much measure. The most of the measure is to eliminate the surface, but that will probably be in dilemma with the original design. For example, you want to make a small design, the surface the surface volume, the area volume ratio will definitely be high. So there's some important process called passivation. Passivation means that we trying to finish the dangling bond with something else. So although it's discontinuous, but the states are all occupied. So the carrier, that means your surface states are all occupied by something else. For gallium arsenide, usually some people trying to terminate with sulfide S. Yeah, that's one probability. Yeah. Or if you can draw something above your surface with a higher energy band gap, make the band diagram look like this. Okay, so although your new surface still has a surface state, But since your layer has a higher band gap, the carrier has a much lower probability to reduce the surface to reduce the probability of the carrier to meet the surface states. Okay, this sounds reasonable and simple. However, how do you know the interface between your original material and your preservation layer are perfect? So that's also a very open question. It's also pretty technological issue. Some of the popular devices called aluminum, but not aluminum, ALD, atomic layer deposition, is also very popular for current semiconductor industry because it grows the layer by layer really slow. The difference between these two tools. PCVD will flow in SiH4 and the O2 plasma into your chamber to make it SiO2 on your surface. But atomic layer deposition also flows silent and the O2 plasma into your chamber to form SiO2. But the difference is PCVD, we flow these two gases at the same time. But in ALD, we flow these two gases at one time. We flow the silent first and take a long time to assure each atom is covered by silicon. Then purge the sample, flow oxygen into that to oxidize every silicon atoms upon the surface. So you are depositing the layer for one atomic layer, two atomic layer, three atomic layer. So to assure the film is conformally deposited on your devices. The biggest problem for ALD is it's really slow. Yeah. Since you are doing flowing two stuff at the same time, you might get a 100 nanometer film in few minutes, or 10 minutes is already pretty slow. However, you're doing aluminum, atomic layer deposition, ALD, depositing a 30 nanometer film is almost impossible. It will take a whole day to do that. So the ALD necessary or is the least and available measure, while you really need the surface to be fully passivated, or you need the layer thickness to be very uniform everywhere. So this is for your information. Okay. Anyway, probably we're gonna just take a okay. 这里先断。